elite 500 world universities and top 100 universities under the age of 50. The university offers over 140 undergraduate and postgraduate programs covering engineering, information technology, applied biosciences, management, social sciences and humanities, and industrial design and architecture. These programs are taught and supervised by highly qualified faculty, majority of whom are PhDs from the world-renowned institutions. The university synchronizes its research endeavors with national and international needs and works in close liaison with the industry partners. The Development of Medical Devices Development Center, MDDC, at NUST is a vindication of that commitment, as it shall help produce cost-effective yet sublime quality cardiac stents and angioplasty balloon catheters under one roof. The Center for Innovation and Entrepreneurship houses Pakistan's first technology incubation center in academia. Till date, over 20 startup companies have graduated from here. Beyond that, NUST's creative potential has had the world amazed many a time. Recently, a team of NUST students excelled at the Stanford Center on Longevity Design Challenge 2017 in California, USA, with its project AIM, a smart wearable device for tremor acquisition and minimization. Over the years, NUST has developed close academic ties with international universities and organizations of repute that not only facilitate two-way flow of knowledge, but also provide students with the exposure of the socio-economic developments occurring in the outside world. NUST takes pride in bringing students from the underprivileged areas into the mainstream of education. One of the university's initiatives is coaching of students from federally administered tribal areas and Balochistan for the NUST entry test. Merit is the only criterion for admission to NUST. Every year, over 60,000 high school graduates apply against a limited number of seats through a very competitive computer-based NUST entry test. As many as 60% of qualifying students hail from lower middle or lower class. NUST supports majority of them through scholarships, fee waivers and various types of monetary assistance, so that they may not have to quit their education for want of financial resources. There are also ample indoor and outdoor sport facilities to cater for physical health of NUSTians. Students exuberantly take part in different sports and display dynamism, resilience and team spirit. On-campus hostel accommodation is also provided, preferably to the outstation students on first-come, first-served basis. In addition, NUST is aligned with the spirit of social welfare. Having made its mark internationally, NUST is fully poised to achieve new milestones. Launch of 2 new campuses in Quetta and Sialkot is in the offing, while efforts are also at hand for the establishment of country's first ever university-hosted science and technology park at the Islamabad campus, which would serve as a huge impetus to national endeavors for economic development. National University of Sciences and Technology, defining futures.
Worthy guests, please welcome on stage the respected Conference Chair, Dean, College of Electrical and Mechanical Engineering, Brigadier Dr. Javed Iqbal, to present his opening remarks on this auspicious occasion.
Bismillah ar-Rahman ar-Rahim. Honorable Chief Guest, Dr. Samar Marikman Nishan Imtiaz, Chairman, Board of Directors, Punjab Mineral Company, Commandant, College of E&ME, Brigadier Muhammad Alamgir, Vice Chancellors, Professors, faculty members, distinguished guests, students, ladies and gentlemen, Assalamu alaikum, good morning, yo base'a, hello, and ni hao. I hope I pronounced it correctly. It is indeed a great honor for me to chair the 3rd IEEE International Conference on Robotics and Automation in Industry. The first conference was held in 2012, followed by second in 2016. I'm very happy and grateful that so many distinguished scholars, researchers have come from both home and abroad to share their knowledge and experience. I strongly believe that realization of our vision at NUST College of E&ME depends on active learning, These conferences help young minds to flourish into active learners and grow into global leaders crossing national and disciplinary boundaries. The International Conference on Robotics and Automation in Industry aims to provide a platform for engineers, scientists, scholars, and students from the university and industry all around the world to present ongoing research activities in the domain of robotics and automation. A total of 180 papers were submitted this year, out of which 54 papers were accepted and will be presented in oral and poster sessions of the conference. IEEE rules and regulations were followed during the review process of the papers. It has been our pleasure to host all the participants and distinguished guests of the conference at NUST College of E&ME from all corners of the world. We have been fortunate to have some of the eminent persons from academia and industry working in the area of robotics and automation. This year's thematic areas of conference are true reflection of the progress made by the robotics community. We'll have some exciting workshop on 3D reconstruction, humanitarian technology support by IEEE, and non-linear dynamics and robotics. Similarly, we'll have seminars on robots in nuclear industry, universal robotics, intelligent automation research, and projects for sustainable cities. Ladies and gentlemen, we have the privilege of having with us our esteemed keynote speakers of the conference. I would like to take some time to introduce them. Professor Peter Koch is a distinguished professor of robotics vision at Queensland University of Technology, Australia, and director of Australian Centre for Robotic Vision. He completed his PhD in mechanical and manufacturing engineering from University of Melbourne. His area of research is robotics and machine vision. He is known for his work in field robotics and development of robotics and machine vision toolboxes for MATLAB. He is also the author of textbook Robotics, Vision and Control. Professor Koch is a fellow of Australian Academy of Technological Sciences and IEEE. He is a founding editor of the Journal of Field Robotics and former member of the executive editorial board of the International Journal of Robotics Research. Our second keynote speaker, Professor Dr. Byrne, has completed his PhD from TUKL, Germany, and is currently serving as a professor there. His research work includes realization of reliable, complex autonomous robotic systems, behavior-based control architecture, as well as different validation and verification methodologies. Professor Byrne is a reviewer of several journal and robotic conferences. Furthermore, he is a member of several editorial boards. He also acts as a reviewer for several national and international funding organizations. He is member of IEEE, member of Executive Committee of the German Robotics Association, and is leader of the Technical Committee for Robotic Systems of the GI. Currently, he is spokesperson of the Center for Commercial Vehicle Technology, ZNT, at TUKL. Our third keynote speaker, Professor Jun Ho, received his PhD degree from mechanical engineering in the field of automation control from UC Berkeley. He is now a distinguished professor at mechanical engineering and director of Humanoid Robot Research Center, Hubo Lab at KAIST. He performed many industry and government research projects in motion control, sensors, microprocessor applications, and robotics. He is especially interested in mechatronics and system integration. He is a member of ASME, IEEE, the National Academy of Engineering of Korea, and Korea Academy of Science and Technology. I would also like to thank NCRA Scientific Industrial Advisory Board members who graced the conference with their presence. I feel honored to introduce our SIAB members. We have the privilege having Professor Kyung Shik Hong with us. Professor Hong is a professor at School of Mechanical Engineering and Department of Cogno-Mechatronics Engineering, Busan National University, Korea. He has vital research accomplishments in the field of automatic control. Professor Hong was also the keynote at our first conference in 2012. It's an honor for having with us again. Professor Jerry Lin is the professor at the National Taiwan University of Sciences and Technology and has extensively worked in the field of industrial robotics innovation applications. Dr. Manoj is a professor at the Agriculture Robotics Center for Precision and Automatic Agriculture Systems, Washington State University, USA. His research area is agriculture automation and mechanism. Many international awards on research in agriculture technologies are on his credit. Mr. Imtiaz Ali Raskar is an entrepreneur, founder, and chair of Raskar Group. Imtiaz Raskar is one of the best-known entrepreneurs of engineering sector in Pakistan. He has been a member of board of several government organizations. I'm sure that participants will be benefited by interacting with these renowned personalities at the conference. Ladies and gentlemen, I would also like to take this opportunity to thank all reviewers and technical committee members for providing their valuable comments in time and help towards selection of quality papers which are being presented in the conference. I would also like to extend my regards to IEEE Islamabad Executive Committee and IEEE Humanitarian Activities Committee for being our valuable sponsor for the conference. Once again, I would like to pay my warmest gratitude to our presenters, keynote speakers, and SIAB members for being a part of this conference and making it a huge success. Thank you, ladies and gentlemen.
Ladies and gentlemen, we have among us a very distinguished personality known for his expertise in robotics and machine learning. Professor Peter Cork is a professor of robotics vision at Queensland University of Technology. He is also our distinguished keynote speaker. I would like to invite Professor Peter Cork to deliver his keynote speech.
All right, the microphone's on. Thank you very much for the invitation to be here. It's absolutely my great pleasure. What I would like to do this morning is talk very briefly about robotic vision, how we create robots with the ability to see. I want to talk about why that's important, about why it's hard, and some steps, some baby steps that we've made in my lab in this particular direction. Okay. It's not going well. There we go. We all know that computers, sorry, this is not working very well. I'm going to try using this mouse. I'm going to go backwards one. All right, excuse the technical issues. We all know that computers are remarkably good at doing things that human beings find to be very difficult. For instance, playing games like chess or the Asian game of Go. What's surprising, perhaps, to many people is that computers and their close brethren robots are really not very good at doing things that a very small child could do. So to pick up some chess pieces on a board, although a computer could play a very good game of chess, a robot today is not very capable at picking up a chess piece off a board, something a young child could do. And chessboards are all different. So we could program a robot that would do this job just once. But human beings have the ability to generalize, to work with not just one sort of chessboard, but with lots of different sorts of chessboards. And that's a capability that's at the cutting edge of robotics research today. All right, we know that robots today are fast and strong and accurate, right? They're fantastic at doing jobs in particular constrained environments like factories. So we see that robots have been successful. It's a 60-year-old technology, very successful at building motor cars, building electronics, and today very, very successful in logistics. So on the right-hand side, what you're seeing are small mobile robots which are helping Amazon to fulfill orders at a scale that's never been possible before in industry, right? So robots are enormously successful in these sorts of very constrained environments. What we don't see is robots that are successful in many other areas of industry and human endeavor. We don't see many robots in manufacturing. So in mining, we don't see them in construction. We don't see very many of them in agriculture. We don't see very many of them in healthcare. So why is that? Why are robots successful in factories but not successful in these other environments? And I would argue that one of the reasons they don't thrive is they don't have the ability to see, to understand the world that's around them. And in the future, we want robots that can help us in more everyday environments. We want robots that can help us in the office, that can help us in our homes. Robots are not going to be able to do those sorts of tasks unless they have the ability to see. So we use vision all day to do all sorts of tasks. We use our sense of vision to help us navigate. We use our sense of vision to recognize people that we interact with. We use our sense of vision to manipulate objects in our world, to pick things up, to put them down. And here are just a few simple examples of the way human beings use vision. On the left-hand side of the screen, you see a young lady solving a Rubik's Cube problem. She's using her sense of vision to understand the state of the cube. In her brain, she reasons about the state of the cube and how to make it the desired state. And then she uses vision to help her manipulate the cube to its goal state. In the top, you see somebody doing crazy driving, right? But essentially what's going on is they're perceiving the world through their eyes. They're making some decisions, and then they're moving their hands and moving their feet in order to drive the vehicle along the road. You know, they're not doing it the way roboticists solve the problem. They're not estimating their pose in three-dimensional space in real time. It's very, very reactive. Information into the eyes, processed in the brain, and actuated through the hands and the feet. And down at the bottom, you see people doing very dynamic tasks like juggling. So they're using their eyes to predict not only where things are in the world right now, but where things will be in the world in the very short-term future. And that's really critical for success in these sorts of dynamic activities. So currently, today, robots lack our visual intelligence, right? Humans cope without knowing exactly where things are because our eyes tell us where things are with respect to us. It's a very different way of thinking about problems compared to the way we do it in robotics. What is this? All right, so vision is a key sensing modality, not just for people, but for all sorts of organisms. And I think the bee is a really wonderful example, right? A very small creature. Its brain weighs only a gram. It's only got 1 million neurons. Compared to me, we've all got about 10 to the 11 neurons. So bee has got a tiny little brain, yet look at what it can do. It can fly from its hive in a particular direction that it was told by another bee using a dance. It can fly in a direction for a particular distance, find a flower, land on the flower, even though the flower might be moving, gather the pollen, gather the nectar, and then fly back to its hive. Tiny little machine with a 1 gram brain. That's fantastic. And it's something that we're not yet able to emulate technologically. And today, in biology, eyes are everywhere. Almost all creatures on Earth have eyes. The only ones that don't are the ones that live in the deepest ocean or in dark, dark caves where there is no light to enable a sense of vision. And so the sorts of eyes, the sorts of visual apparatus that biological systems have is very diverse. From the little bead-like eyes on the scallops, multiple eyes on a spider, compound eyes in insects, great diversity of eyes, because it really is an excellent way to understand what's going on in the world. It's such a good idea that almost all biological systems have that. So we use vision all day for doing all sorts of tasks. What enables that? Well, clearly there's eyes, right? So we've got 2 eyes, which are pretty much like cameras. They're biological cameras. They're very high resolution. They're about 120 megapixel each. And today, that's cameras with high resolution, that's not a problem. You know, we have digital cameras like we have in our phones, very, very common. Some other stuff. We've got some gyroscopes and some accelerometers in our head that tell us how our body is moving with respect to the world. And that helps us resolve the situation when it looks like things in the world are moving. Is that because I'm moving or because the world's moving? The accelerometers in our head help us to break that ambiguity. But here's the thing that's really, really hard that we can't yet emulate in technology. It's our visual cortex. It's the back 1/3 of your brain. All right? It weighs about 500 grams. It consumes 6 watts of power, and it enables us to look around and understand the whole world that we perceive. And that's an amazing thing. And we're not able yet to do that technologically. We're making some steps, and I'll talk about those in a moment. But that's the big difference between a biological system like ourselves and a robot today. Another interesting thing about the sense of vision is it's not just about taking a picture and applying image processing and looking at the answer. The way we do seeing, the way we use our sense of vision to understand the world is an active process. Our eyes contain the highest performance muscles in our body. They can move at extraordinary speed and extraordinary acceleration because they're never still. They're always looking, trying to understand different parts of the scene. And a way to illustrate this is if you take a test subject and you get them to look at a picture and you ask them questions, where their eye looks, indicated by the green line superimposed upon the picture, where their eyes look depends upon the question that you ask them. So your eye isn't taking the whole scene and processing it, it's looking at the part of the scene that's most salient that will best provide the answer to the question that's been asked. So when you say, what are the ages of the people in the picture, your eyes are scanning up and down to see how tall the people are, looking closely at their faces to see if there are wrinkles, to give you some idea about their age. And if you ask about the material circumstances, the person's eye, completely unconsciously, is looking at jewelry, paintings on the wall, the quality of the furniture, all the things that would enable you to answer that particular question. So vision for robots is not easy, and for a number of reasons why that is. And one is because when we look at a scene, there's potential ambiguity. So here, there are some illusions. It looks like there's a hole in the sidewalk. It looks like there's a great big hole through a building, but it's not. It's a visual illusion. So how do you tell the difference between a picture of a door and an actual door? It makes a big difference. If you're a robot, you need to be able to tell the difference. So the appearance of a scene is quite different to its three-dimensional geometry. And this is a really critical problem in robotics. Now, human beings use a lot of experience and knowledge to resolve ambiguities. So here are some simple little tricks that I made, like a little person dancing on my finger, me being very small because I'm sitting at a very big table, and so on. And we know things about the world. We know there are no tiny people. So although we see the picture and we're surprised, initially then our rational brain kicks in and we reason about what's going on in the picture and we solve the ambiguity based on our experience. Another reason that vision is hard for robots is for robots really important to know where it is in the world. And we know where we are in the world by its appearance. We know what our kitchen looks like. We know what our living room looks like. We know what a lecture hall looks like. But sometimes the appearance of a place changes, even though the place does not change. So here are some examples. In the first column, the same place. Once in the daytime, once at nighttime when it's raining. So a computer vision algorithm that can determine that they are the same place, even though it looks very different, that's a hard problem. The second column is the same place. The lighting's changed. One's got shadows, one doesn't have shadows. How do we deal with that in a robot that uses vision to inform where it is and what it's doing? The last one, it's the same place. One it's covered in snow and one it's not covered in snow. So it looks very different, even though it's the same place. So how do we resolve the difference between appearance and place? Very hard problem for robots. Some more examples. And another reason the vision's hard for robots is because of their inability at the moment to generalize. So I could show you all of these coffee cups and you would say they're coffee cups. Even though it's a different shaped cup, different pattern cup, full, empty, different viewpoint, you know it's a coffee cup. But getting a robot to generalize across all these different views and types of object that have got the same class, the same function, still a very, very hard problem today. So we're making progress. So in the computer vision community, we can do some amazing things, and I'm going to go very quickly through those. We have the ability to recognize, detect objects in scenes and classify them. It's not perfect, but it's come a long way. We have the ability to understand pictures, put in an image, and we can automatically create a caption that says what's going on in the image. So we've reduced millions of pixels into a few tens of bytes of very concise information about what's going on in the picture. We understand something now about humans, about their pose, and that's very helpful for a robot that has to interact with people. We have networks that can understand, that can detect the gender and age approximately of human beings. We have the ability to take a picture and turn it into a semantic map, where the value of each pixel no longer is its red, green, blue color. It says, what's the purpose of this pixel? Is it a road pixel? Is it a car pixel, a pedestrian pixel, or a tree pixel? That's really useful information if you're an autonomous vehicle. much more useful than the RGB values of the pixels. We can train networks that can just look at objects that they've never seen before and estimate their pose, which is wonderful if you're a robot that wants to go and pick something up. And all of these innovations that I just showed you from the computer vision community are driven by three innovations or technologies that really are being provided for free to us who are doing robotics. First one's better computers. We don't have to do anything. We just sit back and Intel and AMD and NVIDIA just every year produce better and better computers. That's fantastic for us. We're coming up with better algorithms to process the data using those computer architectures. And today we have huge amounts of online data that we can use to train these deep networks. So better computers, better algorithms, and lots of data is what's driving current progress in computer systems that can understand pictures. And understanding pictures is the first step in enabling robots to see. So it's a good time for us to be looking at this particular research problem. So now I want to talk about a couple of examples from my lab. And the first one I want to talk about is picking things up. I gave before the example of a child picking up a chess piece from a chessboard. A couple of years ago, in 2017, my lab entered an Amazon-sponsored competition in picking things up. We came first in that competition, which was a very happy thing. And this is our robot. It's kind of crude. It's got two sorts of ways of picking things up. It's got a two-finger gripper, and it's got a suction gripper also on its hand. So it looks at the scene, it looks at the particular object, it figures out what's the right sort of gripper to use to pick it up, and then it applies that gripper. So there's some mechanical innovation here in the way we go about picking things up, but there's also some real innovation in the way we understand what's in the scene that the robot's looking at. So here we have a bunch of objects in a container. And our vision algorithm, the results of which you can see on the right-hand side there, is able to draw the boundary around every one of the objects and label it, say what sort of object it is, and how likely we are, how certain we are about that estimation. And that's critical for the robot to be able to pick things up. We have to know what is where in that particular container. And we're even able to train this on the fly. So even with just a few training examples, which is what the students on the right-hand side are doing, just a few training examples is enough to give this network the ability to recognize a new sort of object. So we don't have to train for days and days on thousands of images of the object. We can train on a relatively small number of examples. That's moving towards the long-term goal of what we call one-shot learning, which you can do with a person. You can show a person something once, and then they know what it is forever. For robots, we still need many tens or hundreds of examples in order to train them. Another area that's becoming very important in robotics today is reinforcement learning. And reinforcement learning is almost learning a skill by trial and error. So what you see here is a poor little robot learning to walk. And every time it tries to walk, it gets a score, how well it walks. We know what good walking looks like, but the idea of reinforcement learning is all I have to define is a measure that says how good the walking is. And if it does enough trial and error and exploration, it will eventually learn to walk. I don't have to program the walking. I just have to program a measure that says this is good walking or not. And after enough time, which can be done quickly, conveniently today in a supercomputer, a robot can learn a new skill. And eventually, if we watch this for long enough, you'll see this robot starting to do pretty good walking. It's what we do when we're kids. When we're born, we don't have very many skills at all, but just through lying on our backs and thrashing our legs and our arms around, we eventually learn good skills. We get feedback from our parents and from our own body. When we do something that hurts, we don't do that again. This is what's coming to robotics today, and it's a very, very powerful tool. So we've done some of this work for training robots to do vision-based tasks. In simulation, we simulate the world, we simulate the robot, we simulate the camera, and the robot can just do reinforcement learning. It can explore, and then the tricky bit is to take the skill that it learned in simulation and apply it to the real world. So this is my former PhD student, Fangi, and he trained in reinforcement learning. The robot, a skill is to reach towards a blue cube. So it doesn't matter if there's other things in there that it's never seen before. Wherever he puts the blue cube, irrespective of what else is in the scene, it will relentlessly reach for that blue cube. That's all it does. All it does is reach for blue cubes. But it's an example of a real-world skill that was trained in simulation using reinforcement learning techniques. Another result from one of my current students, Doug Morrison, and he's trained a network that looks at a scene and figures out where's the best place to grab something. So it figures the thing that's most graspable, it figures out how far apart the fingers should be and the orientation of the fingers, and it reaches in and grabs. Even if the scene is moving, it's able to quite successfully pick things up because it makes a decision on grasping in less than 20 milliseconds. It's very, very fast. Bit of a change of pace. This is a robot we developed for environmental monitoring purposes. This creature is a starfish called a crown of thorns starfish, and it devours coral. And so we have plagues of these on the Great Barrier Reef that take a colorful, vibrant coral reef and turn it into a coral desert that you see on the right-hand side there. And in my country, there is a marine science laboratory that developed a toxin that could be injected by a diver into the starfish, which would kill the starfish and save the coral. So there's an interesting moral choice to be made here. The problem is that the Great Barrier Reef is nearly 350,000 square kilometers in area. And so it's not scalable to use human divers armed with injection needles to remove starfish from that whole reef. It does not scale. So what we did was propose a robot, because we're roboticists. So we imagined a robot like this that has cameras that could sense starfish, reach down and inject them. And we built that robot. So this is the vision system of the robot looking at coral. We trained it to recognize starfish. They've got quite a distinctive texture and appearance. We developed an injection system, which is a simple 2 degree of freedom arm on the bottom of this underwater robot that we developed. And in a moment, you'll see the all-up performance of this system. The robot can see a starfish, can reach out and can inject it. So it's a proof of principle that we can have a vision-based machine that can recognize objects in a complex environment and do a useful physical task there. This is the next generation of robot. It looks much more sleek. There are 2 cameras in the bottom, 2 cameras in the front. So it can build a 3-dimensional model of the world as it swims through it. Another robot that we developed is for agriculture. And agriculture, over the last hundreds of years, actually, the productivity of agriculture has improved massively through better plants, through bigger machines, and through pesticides and herbicides. But that's starting to come to an end. And so now there's, how do we get the next lift in productivity on farms? And one way is to remove the labor component. So instead of having people driving machines, we have machines that drive themselves. And instead of having machines that are very, very big, which is what you need to get productivity with human drivers, maybe we can reimagine it to have lots of small machines doing the task that one big human-driven machine used to do. The machines can operate in parallel. If one breaks, you still got the rest of them are working. If you've got a big machine and it breaks, you're stopped. You can't do anything. And so we developed a small modular robot that moves across the field with cameras. It looks down, recognize each individual plant, detects each plant, recognize it, classifies it. Is this the crop plant or is this a weed? And then we can apply very limited amounts of herbicide just to the plants that we deem to be weeds. Not to all plants, but just to those plants. The other thing we can do is instead of applying spray, we can actually pick those plants out of the ground. So we can do agriculture and weeding without needing any chemicals at all. It's just an intelligent system that can control the way it digs plants out of the ground. We can also build up big photo mosaics. We can build a photo map of the whole field that lets a farmer see in one glance what's going on in his productive areas. And the robot's also able to autonomously go back to its house where it can recharge. It's an electrically driven machine. Its house contains solar array on the top. It's able to put itself away and recharge. I'll skip on from there. The last robot that I want to show you is a robot we developed for fruit picking. It's a particular fruit we're interested in. This is what Australians call capsicums, but you might call them bell peppers or red peppers. This is Harvey, our capsicum picking robot. Here he is inside our greenhouse environment. And what you see now is the robot's eye view of the fruit that it wants to pick. It moves around to get a good view to build up a decent 3-dimensional model. On the left, you see a colored point cloud representation of the fruit. It plans a path that goes in and allows the suction gripper to attach to the flat side of the fruit. It then goes in and cuts the stem with a vibrating saw, and the result is that it ends up with the fruit hanging in its hand. It's about half the speed of a human. When humans do this task, they use both hands. They hold the fruit with one hand and they have a pair of secateurs in the other hand and they cut. But this robot is relentless. It'll work 24/7. It would work in the dark and is a viable solution to labour shortages that we face in Australian agriculture today. So, some take-home thoughts. I've covered a lot of things very quickly, but I want you to take away the thought that vision is a technology used by nature to understand the world and enable useful action. It's a powerful sense. We use it, almost all animals use it. We are in existence proof that a robot with a pair of eyes could do almost everything that we do today. So that's the light on the hill. That's the aspiration for roboticists. The lack of visual ability in robots today is holding them back from all sorts of application areas. The challenge isn't in the sensors. The challenge isn't with the cameras. The challenge is in the algorithms that we need to implement to process the visual data, to guide, to command the robot's actions. Deep learning is giving us fantastic progress at the moment. It's a big leap forward, but we're not there yet. Right? There's still work to do. Down the bottom, I want to give a quick plug to an online educational resource I have called the Robot Academy. It's 200 free video lessons across arm robots and computer vision. So feel free to use that resource. I'll stop there. Thank you very much. I think we were doing questions.
Anybody has questions, just raise your hand.
Hello, my name is Dr. Faraz from HIT. I'm just curious about, there was a paradigm shift from structured algorithms towards the use of AI,
Yes.
which were at the expense of accuracy. We got speed in performing certain tasks. So how do you use AI, and what sort of paradigm shift do you envision in the future in this area of machine vision and
You're correct that there certainly has been a paradigm shift away from sort of more classical engineered approaches to approaches where we train computer algorithms to do the job. I think the reason we do that is the performance is astoundingly better with systems that learn compared to the systems that we're able to engineer. So we had a number of revolutions or paradigm shifts in computer vision, feature detectors in the late 90s, early 2000s, SIFT, SURF, and so on. But the shift from engineered features, engineered algorithms through SVMs to current deep learning, it just has been continuous progress. The thing that worries me about any learned system is that we're unable to really say anything very profound about its performance. We can say that its accuracy is maybe 97%, but we only say that across a particular set of images, right? In the general sense, we can't really predict how it will work with an image that it's never ever seen before. They seem to have a good ability to generalize, but we also know that they're very easily spoofed and fooled. And I think this is a big worry when we put a network that's being trained in charge of a machine that makes physical action in the real world. And this is an area of current great research interest. We call it explainable AI and other terms like that. So how do you get an AI system that says there's a particular thing in the world? Then we can ask it to introspect and tell us why it believed that that's actually the case. So I think there is a trust issue around a lot of these deep learned systems, and we haven't seen any of them yet in production. And I think it's because of this, because we're not able to trust them. We don't understand why they give us the answers that they do. and that's a little troubling. But the performance that they offer is impressive and it's very seductive. So I don't think we'll come back from the path of deep learning. We're just going to have to do it better.
Thank you, Professor. I am Mohammed Siddiqui, and I am a graduate student here in this college. So my question is that you showed us a slide in which you showed us that a robot is learning how to walk.
Mm-hmm.
So the question is that we know how to walk.
Yes.
So why a machine or a robot should learn itself? What is the benefit of that? Why cannot we transfer our knowledge to it?
I think that your question is at the heart of a raging debate in robotics at the moment. It's about the people who believe you should learn everything versus the people who say we have good models of how things work. We know about dynamics and kinematics. Why should we throw away all of that knowledge and learn everything? So there is really a dichotomy in the field at the moment. And I would say this is a broad stereotype. Computer science people tend to want to learn everything, and engineers want to use as much traditional mechanics, physics knowledge as possible and fuse that in some way with what a network can learn. So there are two different ways forward. I don't think at the moment we know which is the best way forward. I consider myself somewhat old-fashioned. I can't see the point of learning things that we already know. Why should a robot thrash around for hours or days or weeks to learn Newton's law? We've known that for hundreds of years. The robot should know that as well. Question over there.
Assalamu alaikum. My question is that why do we need to teach the robot to walk? Why don't we develop any alternates? For example, shouldn't the robot know how to hover?
Sorry, could you repeat your question?
I'm saying that why should the robot walk? How about we start developing alternates? For example, if the robot starts to hover, then that should solve this problem.
I'm sorry, I don't quite understand the question. Can someone else perhaps rephrase? You say, why walk? Why don't use other modes of locomotion? Yeah, absolutely. I mean, in the robotics field, there are people working on all manner of alternate locomotion techniques, from wheels, from flying, to hopping, jumping. There's many modes of locomotion. I guess we know that legs are effective. We know that human beings with legs can walk over a hugely diverse range of terrain. And that's probably the motivation why people are focusing on legged locomotion. But it's not necessarily the best, but we know it's versatile. There is an existence proof that walking machines are walking organisms. It's a good way to get around.
But you know, if
okay, just one question per participant because there's a lot of people.
We can talk about this offline.
Yeah. Okay. So I've got a question as well. It's regarding the submersible machine that you showed, the one that's injecting the starfish. Now, okay, so for processing, you usually need a computer. You yourself said, okay, sometimes we need a supercomputer to resolve problems. Now, that was a dynamically changing environment, and again, it was underwater. And and you're doing it on an embedded platform.
Correct.
Within the robot. So what are the challenges that we should look forward to face if we want to actually develop such sort of a system?
So to put a deep learned classifier, which is one that robot has, there is a deep network that we train to recognize starfish. To put that on an embedded platform, there are a lot of trade-offs, right? You've got an architecture. It's an NVIDIA Jetson in there. It's got a high power consumption. The more power that you put into the computer, the less distance you can move for a fixed size battery. So power trade-off is one. Next one is that we wanted to get about 10 updates per second. So that means we had to simplify the network. We had to throw away layers. We had to make the layers smaller, right, in order to get the sample rate that we desired. So it's a big exercise in trade-offs. And there's quite a lot of research these days about how you take a network and how you can simplify it by quantizing the weights, throwing things away that are small in order to get them to run now on quite small computers. So there are programs that take a network and make it work on very small embedded computers. So it's an important and interesting area that makes these deep networks accessible for real-world applications. Still need a supercomputer to do the training, but the runtime inference can be done on quite a modest platform today.
Sir, up here, sir.
Okay.
Sir, I got a question. It's regarding deep learning.
Yeah.
So in deep learning, like it's a theory that if we give robots a little too much freedom, they would find a way to that they would think we humans are interfering with them, and they would try to kill us. Like they would see us as interference in their work, and they would say to be more, productive, we humans have to be eliminated.
So it sounds like a Hollywood movie plot. That's Look, humans are worried about this for a long time. The story where the term robot was first coined was written by a Czech playwright, Karel Čapek, in 1920. The next year is the 100th anniversary of the story, the play, which has human beings creating robots and then the robots not liking the humans and killing them all. And then we keep seeing this movie made over and over again, often with Will Smith in it, right? So I don't know, it's something I think all humans have a fear of the other, whether it's a different race of person or a different type of person. You know, some people are saying that robots are another sort of group of beings, maybe they're beings from the future, that we just react badly to. I think it's quite wide in our nature to be worried about people who are not quite like us. Right now, today, robots are very far from having that ability. It is something that we will need to worry about over the coming decades. So maybe in your lifetime, this will be an issue, and we need to find ways, create frameworks, ethical guidelines for the way we program robots. As a colleague of mine said the other day, if you're worried about the robots coming to take over the world, you just close the door, right? Because robots are not very good at opening doors, right? So not a problem today, but it is a problem that we need to be very vigilant about. True. So Asimov did pose 3 laws of robotics, and at face value, they look like very sensible laws, but they're not perfect. And so Asimov was able to write hundreds of books, right? Because the laws are not quite perfect. So we could always find a loophole or a corner case or a bad interaction between the laws, which would let something weird happen. If the laws were perfect, he wouldn't have written any books. He'd written 1 book, not all the ones that he did write.
Thank you, Professor Peter. My name is Abbasi. And I want to listen your comment that aren't we asking too much from the robotics, because we are still not aware of the complete knowledge of human visual system and how the human vision process itself. Mm-hmm. So I think our expectations are too much from robotics vision. What is your comment on that?
I think you are probably correct that our expectations of what can be done, I think, are exaggerated. I think there is a lot of hype in our field that makes promises that we cannot deliver. Your comment about the human visual system, I think, is an important one. And there are massive projects today, particularly in Europe and the United States, to basically map the neural structure of the human brain. I think once that's done, I think we will understand a lot more about the algorithms that are embedded in the human visual cortex. So I think that's a wealth of data and knowledge that we have to look forward to over the coming decade. There'll be amazing tricks in there, and we'll look at the way our brains are wired and say, that's a good algorithm. I'm going to code that and put that into my robot. So that's for our future.
Okay, I have a question. It appears that you're focusing more on computer vision, mm-hmm. But there has been a lot of research in sensing technologies, like they inject a helium isotope to get more visibility into what is happening in the body. So do you think that augmenting vision, different senses can help you more in doing what you intend to do?
Absolutely. So the whole history of robotics has really been driven by innovation in sensing. So 20, 30 years ago, people were using ultrasonic sensors, and we have LiDARs, we have radars. There's a huge range of sensors that are available to us. Each sensor has got an advantage and a disadvantage. And I think, to me, the advantage of vision is it allows me to see what's up close. It allows me to see all the way out to the horizon. It's sufficiently rich in resolution to enable me to determine the three-dimensional shape of things, which is important in order to manipulate them. I can recognize faces. I can recognize the emotional state of those faces. So it's a very versatile sensor. And we know that cameras themselves are ridiculously cheap. I mean, Apple is probably buying cameras for 50 cents each and embedding them in iPhones and tablets and whatever, right? So we know that the fundamental sensor to enable a sense of vision is very, very cheap. The problem is simply algorithmic. And so given what we know is happening with computation and the cost of computation going forward, there will be a point in time at which a cheap camera chip with a cheap neural processing engine is going to be able to give us information about the world comparable to what we get. That time will come. It is inevitable. That's by looking at technological trend lines. So I think that's the reason that I'm really interested in vision. It's a non-contact, non-invasive sensor that potentially gives us almost all the information we want to know at the world for navigation, manipulation, human-robot interaction.
Okay, so we're going to have just one last question from over here, and then the professor is here for 2 days, so everybody's going to get a chance to interact with him, and you can ask your questions during the 2 days of the conference. So just one last question from over there.
Okay, my name is Dr. Yasiniaz Khan from University of Lahore. So I'm a roboticist as well, and wherever I go to give a talk, I got a question about jobs.
Yep.
So let me rephrase that.
You're going to ask me the jobs question?
At the one hand, we have rich countries who say we have a shortage of labor, and on the other hand, we have poor countries who say we have a shortage of jobs. So instead of focusing on like agriculture or picking of fruit, shouldn't we first focus on, for example, hazardous jobs like nuclear plants or coal mines, and instead of taking jobs and there we can employ the people of poor countries first before turning our robots to those areas? Do you understand?
It's a good question. It's a conversation we should have, but I don't think we've got enough time to do that conversation properly. Every country has got different constraints. So Pakistan is probably unusual in having a very young population, growing population, and very young. For almost all the world, big Asian countries, Europe, United States, my country, our populations are getting older. And so what worries us is the productivity gap. There's going to be a large number of elderly people, less working age, young people to look after them. That's something that scares all of those other governments. So that's one reason that we're looking at robotic technology. In my country already, we have problems with labor availability. It doesn't mean everybody's got a job, but it means that today people are unwilling often to move outside the city to get a job. So if they live in a city and they don't have a job, there's a job in the country, right? So what do we do about that? If we've got farms in Australia that can't get people to harvest the crop, and the crop rots on the bush because no one harvests it, that's not a good thing. So from the point of view of Australia, what do? We could have guest workers. Politically, in my country, that's almost unacceptable. This is a very touchy issue with many countries, right? So guest workers isn't going to work. Another option is we could just import all the fruit and vegetables. We don't grow anything in Australia, we just import it from other places. That doesn't seem like a very good solution. The third solution is we grow it at home, but we use robots to help harvest the fruit. That seems like the best solution. There are more jobs that could have been taken by humans. If the humans don't want the jobs, what should we do? So, it is a complex issue, and it does depend country by country. I think also a lot of the headlines that we read, 40% of jobs will disappear by the year 2030. This headline keeps coming up. Even the people who wrote that original report at Oxford no longer believe that. I think what we will see artificial intelligence remove a large number of white-collar jobs before robots start to take blue-collar, jobs, labeling jobs, agricultural jobs. So I think actually AI is probably the big job remover that we should be worried about today. But I'm happy to talk more about this offline. Thank you. Hi. That was a bit lumpy to start with.
That was great. I liked it.
Thank you. I think I didn't have enough range on this.
Thank you, sir. Ladies and gentlemen, we are delighted to present our esteemed guests with souvenirs as a token of appreciation. For this, I would like to request the chief guest, Dr. Samar Mubarak Mand, and the Commandant to please join us on the stage.
Yeah. I'll come and do it at the break time.
Okay.
Yeah.
First, we shall present the souvenirs to our respected keynote speakers. Please welcome on stage Professor Jun Ho Oh to collect his souvenir. I request Professor Peter Cork to kindly receive his souvenir. I would like to call Professor Karsten Burns to accept his souvenir. Now, we would like to extend the souvenirs to the members of the Scientific Industrial Advisory Board of ICRAI who have graced us with their presence today. I would like to request Mr. Imtiaz Ali Rastgar to come to the stage to collect his souvenir. I would like to call Professor Manoj Karki to accept his souvenir. And finally, please welcome on stage Professor Huim Shik Hong to collect his souvenir. Now, I would like to request the Commandant to present this token of remembrance to our esteemed chief guest. I request the Honorable Chief Guest to kindly deliver his conference address.
The Commandant, the foreign participants, keynote speakers, delegates to the conference, students. I am very honored to be at this institution today. Um, I've seen 3 of my children pass through this institution, degree 7, degree 17, and degree 19. And now this present conference gives me an opportunity to thank the College of Electrical and Mechanical Engineering, and especially your robotics department, for organizing this conference on a subject which is very vital for the future of the country, for the future of society, and it will also be of interest to interact with the foreign delegates and see what the world is doing about robotics and automation, and how we can benefit ourselves from it, how the students can feel inspired about the new avenues of research and development, and what we can do to adapt them to our national solution of our national problems. Just let me recount that when I was doing my PhD at Oxford, it was the decade of the 60s, and my supervisor told me that we have to go and visit a science exhibition in London where the transistor was at display. We have been working with power valves, glass valves, and tubes were operating at 300 degrees DC voltage, but suddenly we saw this development of the transistor through the solid state physics development of materials. And then later on, 20 years later, the microprocessor was invented. And with the invention of the microprocessor, the computers became miniaturized, became faster, and their applications became very versatile. All over the world, you could see computer applications in communications, in medicine, in agriculture, in defense, and so on. So all these things have been possible with a joint effort of physicists, of the electronics engineers, and of the electrical engineers and the mechanical engineers. What we are discussing today, of course, a lot more has happened in the world besides this, what we are talking about. But this is more or less an amalgamation of. And then, of course, if you look at the biosciences, then it is the biologists and the medical people who have also contributed to robotic applications in their own field. We can keep talking about there are millions of applications of microprocessors and robotics we see around the world these days. The salient applications are, of course, but whatever we heard in the keynote speaker talk about, it became very apparent that at the front end you have sensors like the eyes, you have the ears, you have the smelling sense, which receive signals from what they see, what they apprehend, what they sniff around, what they hear. And then at the back end, this data goes into a microprocessor or a fast computer or a brain, and this then is programmed in a human being. The programming is done by nature, and in the man-made machines, it is the algorithms. As best and as fast as you can make them, the more versatile will be the machine, and that more will be the capability of that machine. So this processes the data of the sensors and then gives a decision to the mechanical side, to the actuators, to operate the arms, to operate the hands, to do what the brain has or what the computer has decided should be done. So it's again the sensors see what is being done and give a feedback whether it is being done rightly or wrongly or properly or not. So this is a feedback control system which is operating with sensors on the front end, then there's a brain at the back or a computer at the back, and then there's a mechanical part of it. So this is how robotics work. But we have been talking about robotics today, but there was a apprehension that one day they are going to take over the human beings and start killing them. But the point is that today we see the applications of robots in manufacturing plants, in car industry, for example, they're putting components in and out, they're machining components and so on automatically. And this leads to competitiveness in industrial production. There is less loss through quality rejection. There is faster production, but then the human resource can be laid off, and you can use the machines for automation. So this is an ethical problem also which arises out of this. But on the other hand, we can also use these same robots to replace normal human functions. One could say, why make the human beings redundant? But look at the applications of the people who have active and live brains, but the bodies for some reason have been paralyzed. And these robots which you create to perform human body functions will become extremely vital and important. And this friend of mine at Cambridge who spent his life paralyzed, and he would just think things, and the voice was there, and the actions were implemented, and he was doing a remarkable job in physics and astronomy for the last 50 years, till his demise a year or so, 2 years ago. So all this becomes important when you try to emulate the human body functions with a robot. So it is not always going to be a negative impact on human existence by the creation of robots who will do human body functions or even thinking. In applications in defense, a remarkable application is a cruise missile. Since I've spent half of my life in this field, the cruise missile has a sensor at the front end. It's a camera which has a night vision capability and of course a day vision capability. And as the missile flies, of course there's a GPS system, or you can say a sensor which measures the latitude, longitude, position coordinates of the flying machine. It gives that data to the flight computer on board. The computer processes the data and then determines the lat-long coordinates of the machine. And then it compares these coordinates with where it should be as far as the map stored of the map of the world in high resolution stored in that computer. It compares the two things, that the position is right or it's deviated from the place where it should be, and then gets signals to the sensors to change the ailerons or the rudders to bring it back to the right position and keep it on track. So that is beautiful. But then when this approaches a target at night, for example, or daylight in hours, then the camera sees the object, then performs image comparison, because the image of the object is already stored, the desired object is stored in the camera, in the computer. So it does the image comparison and directs the cruise missile onto the target accurately. So this is all being done here in our country, and by students who were maybe 15 years senior to you, but it's being all done here without any external help. And it's the innovation and the hard work of graduates from, most of them are from this institution, because you are in Islamabad and NUST is in Islamabad, and the whole work is being done around here. So most of you will get opportunity to do all what the country needs in the future. My great appreciation and thanks are for the keynote speakers who have come a long way to come and share their knowledge, share the technology of their innovations, to share the technology of their inventions and the development with our own local scientists and engineers. And also this process of friendship. As you see, one of the speakers came here in 2012, is back here again now, the keynote speaker, I think from Korea. So this process gives birth to a friendship, a lifelong friendship, but it's a professional friendship, and it's an academic friendship which you share and sustain in the years to come. And the students are, of course, inspired by this. And when you get into these research projects, these students I'm talking about, then you will learn very fast, and you will learn a lot in different fields. As I said, in mechanics, mechanical engineering, in software engineering, in electronics and electrical engineering. And you will learn to, of course, program your computers and develop algorithms also. So all these things have to be done to develop your robotics and automation systems, which will be of great benefit to the industry and to the country. The faculty of this college is working very hard, and they deserve the accolades of everybody here around here, and me also, that they have guided these students and inspired them to work on these projects. I visited your robotics lab about 2.5 years ago, and it was still in infancy, but now I think you are publishing very, very beautiful papers and in abundance. And I think you are now you have picked up momentum, and you are well on your way to doing very good work in the future. This college, this E&ME college, is a platform which is providing this opportunity to all of you to do this work and to learn all this knowledge. And we are all, as a nation, grateful to this institution, and of course to its leadership, to have the vision, to have had the vision to move from Quetta to Islamabad, to Rawalpindi, and provide the opportunity to, and of course your campuses at Quetta and the other campuses, I don't know where you're talking about. These new campuses also will give benefit to the students in those areas also. So I'm very glad to be here, and I'm honored to be here and meet all the people who are participating. Thank you very much.
Ladies and gentlemen, you are requested to rise for the national anthem. Ladies and gentlemen, it has been exciting to have you here. We thank you for your presence. I request the guests to please proceed for the refreshments.